So problem states that it is known of a polynomial over Z that P of n is greater than n for every positive integer n. Consider x1 is equal to 1, x2 is equal to P of x1, and we know that for any positive integer capital N there exists a term of a sequence which is divisible by n. So prove that P of x is equal to x plus 1. So the first thing that we know is P of n is greater than n for every positive integer. Positive integer. And there we have a sequence x1 is equal to 1 and x2 is equal to P of x1 and x3 is equal to P of x2, and it will goes like this. So basically this is a infinite sequence, and each term of a sequence is a positive integer. Now there is some capital N for which xi is some term in a sequence which is divisible by this n, and I is from the set of natural number, right? So there is a one lemma that is useful to solve this problem, which states if a and b are two integers, obviously they are two distinct, then a minus b divides p of a minus p of b. And except this, our second proposition is if a divides b and b divides c, so the resultant would be a divides c. So we are going to use these two propositions, and now let's take a look in this lemma. Since x1 and x2 are positive integers, so we can say that x1 minus x2 must have to divide p of x1 minus p of x2. And since we know that p of x1 is nothing but x2 and p of x2 is nothing but the x3, so we can put the value and we'll get that p of x1 is x2 minus x3. Similarly, we can say x2 minus x3 divides p of x1 minus p of, whoops, I made a mistake, p of x2 minus p of x3. So we can say x2 minus x3 divides p of x2 is x3 minus p of x3 is x4. And one thing that we know, this is our third proposition of this problem. If A divides B, then A, absolute value of A must have to be smaller or equal to absolute value of B. And now if we use this proposition, over here, then what we get, so what we get, that mod of x1 minus x2 is smaller than or equal to mod of x2 minus x3, and this will is smaller than or equal to mod of x3 minus x4, and it will continue, right? And simultaneously I want to use my second propositions, which states if A divides B and B divides C, then A must have to divide C. So if we see that x1 minus x2 divide x2 minus x3, and x2 minus x3 divides x3 minus x4, then the resultant would be this, means x1 minus x2 divides x3 minus x4. And we know that this is an infinite sequence, so we can generalize this statement and say that any two consecutive term will divide another two consecutive terms, where the condition over the index is I must have to greater than n. Here this must be, I think it's not strictly, or maybe equal to n, right? So fine. Now if we look back to the problem, so for any positive integer n, there exists a term of a sequence which is divisible by n. So now we're gonna use that information, that for n there must be an element, let's say it's xm, which is divisible by this n. So now what we can say, and by the above result we can say that this xn minus 1 divides xm minus 1, and this will imply that xn minus 1 separately divides xm minus 1. And if you see, then we can continue this by saying that xn minus 1 divides xm minus 1 minus xm minus 2, because these are two consecutive distinct terms again, so it will follow this result. Whoops, sorry. Yeah, this one. And this will imply separately again xn minus 1 divides xm minus 2, so it will continue, we can say this. So finally, after doing this several times, and we can say that xn minus 1 will divide xn itself, because here we know that I could be equal to n. So obviously, if you backtrack, then m to m minus 1 to m minus 2, then it will end up here at n. So this is again very obvious thing. And now we know that any integer or any number will definitely divide itself. So this implies again that xn minus 1 divides xn minus 1 separately. And now use the third proposition, and we can say that xn minus 1 is smaller than or equal to xn minus 1. Remember, I not used here the absolute value sign because we know that this sequence is strictly increasing sequence, and if we take two consecutive terms and take a difference from bigger value to a lesser and take a difference, then it would be a positive result. So I not taken the absolute value over here, and we know that simply we can write this like xn minus 1 and 2 over here. So this is the inequality that we obtain, and we can simply say that xn is nothing but the p of xn minus 1, and which is smaller than or equal to 2 of xn minus 1. So here we get p of x by just replacing this xn minus 1 is smaller than or equal to 2 of x. And at the beginning we have seen that Pn is greater than n. This is here. Pn is greater than n, we already know. And certainly we'll use this to make a inequality, and we can say that this is greater than x. And now what we can say, x belongs to positive integers. So this is our inequality